Hello students, today in our lesson work, energy and power, we are going to see the topics of kinetic energy, work, kinetic energy theorem, relation between momentum and kinetic energy, then potential energy, potential near the surface of the earth. Come, let's get into the subject. Kinetic energy. See, kinetic energy is the energy possessed by the body by virtue of its motion. All moving objects have kinetic energy. A body that is in motion has the ability to do work. For example, a hammer kept at rest on a nail does not push the nail into the wood, whereas the same hammer, when it strikes the nail, draws the nail into the wood. You can see that in the small GIF file. Kinetic energy is measured by the amount of work that the body can perform before it comes to rest. The amount of work done by a moving body, it depends on the mass of the body and the magnitude of its velocity. A body which is not in motion does not have any kinetic energy. Now, an important theorem which is work kinetic energy theorem. Work and energy are equivalents. The amount of work that the body can perform before it is work done by the constant force F. For a displacement S, which is represented by the term S, and it is in the same direction. Therefore, work is equal to displacement into force. Let us have this as a equation number 1. The constant force is given by the equation. This equation is from the Newton's second law of motion. F is equal to mass into acceleration. The third equation of motion can be written as, which is v square is equal to u square plus 2as. If you take the acceleration here to a, then you can have the v square minus u square into left hand side, which is divided by the 2 and s. So a is equal to v square minus u square divided by 2s. Now, substituting the value of a here in equation 2, you get f is equal to m v square minus u square divided by 2s. Let us consider this as equation number 3. And we got the value of f now. So we can substitute this value of f in equation number 1. If you substitute this in equation number 1, we get w is equal to m into v square by 2s into s minus m into u square divided by 2s into s. Let us have this as equation number 4. So finally, which is w is equal to 1 by 2 m v square minus 1 by 2 m u square. Therefore, the expression for kinetic energy, you can have the term 1 by 2 mv square in the above equation is the kinetic energy of the body of mass m moving with the velocity v. Actually, this is the final velocity. V is the final velocity and u is the initial velocity. So, final velocity minus initial velocity. So, finally we get the v. Therefore, kinetic energy is equal to 1 by 2 mv square. Kinetic energy of the body is always positive, and from equation 4 and 5 we have del Ke is equal to 1 by 2 mv square minus 1 by 2 mu square. Thus W is equal to del K into E. This expression of the in the right hand side, that means this, from the equation 6, 1 by 2 mv square minus 1 by 2 mu square is the change in kinetic energy del Ke of the body. This implies that the work done by the force on the body changes the kinetic energy of the body is called work kinetic energy theorem. This work kinetic energy theorem implies some important issues. They are: if the work done by the force on the body is positive, then it is kinetic energy increases. If the work done by the force on the body is negative, then its kinetic energy decreases. If there is no work done by the force on the body, then there is no change in its kinetic energy, which means that the body has moved at constant speed provided its mass remained constant. Now let's see the relation between momentum and kinetic energy. Consider an object of mass m moving with the velocity v vector, then its linear momentum is p is equal to mv, which you know already, and its kinetic energy. Therefore Ke is equal to 1 by 2 mv square, and Ke is equal to 1 by 2 mv square minus 1 by 2 m into v vector into v. We divided this v square into v vector into v vector. Let us term this equation as the first equation. Multiplying both the numerator and denominator of the equation 1 by mass m, then we get Ke is equal to 1 by 2 m square v vector divided by m, and you can split it into 2. That means the 1 by 2 into m v vector m into v vector dot m into v vector divided by m. As you know, p vector is equal to m into v vector from the linear momentum. So we got 1 by 2 p vector dot p vector divided by m. That is equal to p square divided by 2m, and kinetic energy is equal to p square divided by 2m. That means where p is the magnitude of the momentum, the magnitude of the linear momentum can be obtained by p vector modulus is equal to p is equal to root 2m Ke. That means we take this 2m into left hand side. Therefore p square is equal to 2m Ke. If you take the square out, then it will become a root for this 2m and Ke. In this picture you can see the movement of a object through in a plane. If it moves down, initially when it starts it has a potential energy. If it moves down, it loses potential energy and it got gained in the kinetic energy. Finally, altogether this potential energy and kinetic energy totally termed as the total energy, which you can see here. While it's rotating, it have potential energy, and if it down, it got its kinetic energy. Potential energy. The potential energy of a body is associated with its position and configuration with respect to its surroundings. This is because the various forces acting on the body also depends on the position and configuration. An object can store energy as a result of its position. For example, the heavy ball of a demolition machine is strong energy when it is held at an elevated position. This stored energy of position is referred as a potential energy. Similarly, a drawn bow is able to store energy as a result of its position. When assuming its usual position, that is, when not drawn, there is no energy stored in the bow, and the potential energy of an object at a point P is defined as the amount of work done by an external force in moving the object at constant velocity from the point O, initial location, of the point P, which is the final location. At initial point O, potential energy can be taken as 0. Mathematically, potential energy is defined as a U is equal to F vector A into dr vector, where the limit of integration ranges from initial location point O to final location point P. You can see here, if it drags on a mountain, it is potential energy, and if it moves to down, it is the kinetic energy of that same object. Various types of potential energies. The energy possessed by the body due to gravitational force gives rise to gravitational potential energy. Then second one, the energy due to spring force and other similar forces give rise to elastic potential energy. The energy due to electrostatic force on charges gives rise to electrostatic potential energy. See, in this picture, actually the stored energy of a position is referred to as a potential energy. So similar, a drawn bow, here you can see in this picture, a drawn bow is able to store energy as the result of its position. When assuming its usual position, that is, when not drawn, okay, there is no energy stored in the bow. Yet when its position is altered from its usual equilibrium position, the bow is able to store energy by virtue of its position. This stored energy of position is referred to as a potential energy here in this bow and arrow experiment. Actually, the potential energy is the stored energy of position possessed by an object. Here you can see in this picture a boy or a girl which you are standing in this slide here have some one at a higher altitude. That means if he is in the top position, he have a greater potential energy. Okay, this boy have a greater potential energy, and the potential energy can be transferred into kinetic energy while he is sliding down. Next one, potential energy near the surface of the earth. The gravitational potential energy U at some height h is equal to the amount of work required to take the object from the ground to the height h with constant velocity. Mass m being moved from ground to the height h against the gravitational force. The gravitational force Fg, which is acting on the body, is F is equal to minus mg, because it is taken up to the certain height position. As the force is in y direction, see, this force is in y direction, the unit vector j cap is used. The negative sign indicates that the force is acting vertically downward. Now, in order to move the body without acceleration or with constant velocity, an external force is applied. That force is Fa. Here you can see the external force, which is equal to in magnitude but opposite to the gravitational force. This Fa is equal to in magnitude but opposite in the gravitational force, which is applied to the body. That means Fa is equal to minus Fg. This implies that Fa is equal to plus mg cap. The positive sign here in this implies that the applied force is in vertical upward direction. Hence, when the body is lifted up, its velocity remains unchanged and thus its kinetic energy also remains constant. The gravitational potential energy U at some height h is equal to the amount of work required to take the object from the ground to that height h. So we get U is equal to integral Fa dot dr, which is equal to integral from 0 to h. That means we are taking the height from 0 ground position to the certain height h. Fa vector modulus into dr vector modulus into cos theta. Since the displacement and the applied force are in the same upward direction, the angle between them, that is the theta, is equal to 0 degree. Therefore, cos 0 degree is equal to 1. So, Fa modulus is equal to mg and dr modulus is equal to dr. Then we get U is equal to mg into integral 0 to h dr, and we put the potential energy value as mg or 0 to h, that is mgh. So finally mgh is the expression for potential energy. Note, the potential energy stored in the object is defined through work done by the external force and which is positive. Physically, this implies that the agency which is applying the external force is transferring the energy to the object, which is then stored as potential energy. If you take a brick piece or some stone to a height of the building, that means first floor or to second floor, then you are carrying energy for that object. Then if you throw the object from the top of the building, the potential energy becomes nil, and again the kinetic energy come into contact. While it reaching the ground, the ball, brick or a stone will have some kinetic energy, and due to that kinetic energy it will make an impact in the ground like this. If the object is allowed to fall from a height h, then the stored potential energy is converted into kinetic energy, and that kinetic energy will do some impact on the floor. Thank you students, study well.